Hello.
Sir, yes,
Hello.
yes.
Yes, sir. Am I audible?
Sir, yes. Audible, sir, audible.
Okay.
Yes, sir, we'll start. Visible, sir. Sir, any problem?
Hello. Oh, I'm sorry. I was on mute, sir.
Oh, started now. That's why I'm waiting.
Yes, 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 yes. Okay, okay.
Okay.
Sorry.
Uh,
So,
uh,
yeah. So I'm audible, right?
yeah, sir, audible, audible.
Okay, okay. So, yeah. So if the participants have any queries, they can stop me in between and raise it. As you've been doing it, it's really helpful, and I uh, even feel happy that if there is interaction. So we understood how deep neural networks have evolved from the neural networks concept by introducing many more hidden layers in between. And in a way, we also have understood how the network can directly learn from data without requiring any sort of feature extraction or pre-processing or a specific selection of a classifier like we do in the case of conventional machine learning, right? And later we understood how image based data, I mean whenever the data is image, we can build a deep neural network. Instead of using fully connected layers as hidden layers, we can think of a spatially connected network through the convolution layers, right? So we understood how convolutional neural network can be built and what exactly the convolution operation is and how it is going to help in representing the images and the objects inside the image, and the other essential layers like the subsampling layer. For example, we saw how to use max pooling. There are, I mean, max pooling is one way. There are other ways to do so. Like you can choose to go for min pooling. It's not so much relevant. Average pooling is also there, but max pooling has helped in a lot of use cases. So max pooling is pretty, um, you know, useful. And also that we've understood how to uh, put a fully connected layer at the end of a convolution neural network so that the final fully connected layer can be used for the purpose of classification. Right. So in this session, let's try to understand a couple of notable CNN architectures, like the very first architecture which was produced after deep learning was evolved or it became you know very well known, was Lenet 5. So Lenet was proposed by uh, Lee Kun in 1998. So it was 5 because this it has 5 layer depth, and you know it was used for the purpose of the character recognition, especially for the MNIST database. So if you see this is a simplest deep learning architecture, but it was the very efficient architecture at that time, and even till today, this is one of the you know known architectures. So if you try to understand this Linet 5 convolutional neural network for character classification, so it is built out of a sequence of convolutional and pooling layers. So just if you see this, it has a convolution layer followed by pooling, again a convolution and pooling, then fully connected, more fully connected, and at the end, the softmax layer. So softmax is a layer used for the classification problems, wherein it converts the activations into probabilities, meaning each neuron in the softmax layer corresponds to one category, and that uh, when you process a sample through this network, the softmax layer makes sure that the output that is generated out of this layer, suppose if you assume this character recognition problem, and if there are 26 characters to be recognized, so this layer will have 26 neurons. But after the image is processed, the result or the values that you get out of the softmax layer, when you sum up them, it will turn out to be 1. So that is the uh, total probability. So the total probability of different events should be 1, and the one which has highest probability. So suppose if this is k, then the corresponding neuron will be having higher probability compared to other neurons, and that is why softmax is used. And the neuron which has highest probability will be chosen, and the corresponding category label is used as the category of the, I mean, that is the prediction that the network has given. Okay, so that is how it is built. And if you try to look into details of the convolution, it has convolution filters of size 5 cross 5 with stride 1, and subsampling layers for of 2 by 2 with stride 2. That is common all across all the convolution and pooling layers. And fully connected layer, anyway, they will not have any filters. They are just, so once you reach this last convolution layer, right? So this convolution layer, suppose if it is of size 16 by 16, then this will be flattened into one dimensional vector, means it will be uh, 1 into 1 by 256 one dimensional vector. So such one dimensional vectors will be used for fully connected layers. Okay. So that was the initial notable network in the CNN space. And then later in 2012, a network architecture was proposed, which was actually like, which was the winner of the competition at that time in 2012, called as AlexNet, proposed by Alex and Chris Work in 2012. So this was the very first most popular network after Lenet. At the time of Lenet, GPUs were not available for computation. They were not so much popularized, or they were not. They were in the initial stages. So by the time 2012, GPUs were used for computations apart from graphic and gaming purpose, and these guys have started using GPUs for the computation instead of CPU. Thereby, they could think of building a very big architecture consisting of 5 convolution layers, and with a mixture of normalization and pooling layers. So it is just that you see this is going as a parallel architecture, but it is their implementation strategy. So to divide the computation load into two different GPUs, this was done. But all in all, if you try to observe this, it is a sequence of convolution and pooling layers along with a layer that is introduced, which is normalization layer. So normalization layer is generally used in between uh, the hidden layers, typically to normalize the values in the feature maps. Because like every time a layer is generated, a feature map is generated, the feature map typically will have the activations, right? Used generated by the previous layer. So those activations, if you want to normalize all across that feature map, you can use a feature normalization layer. So this will help the network to be fitted into a specific, you know, uh, specific distribution, so that the feature weights can be appropriately tuned. Okay, so the first layer, so here they went with bigger sized filters compared to the Lenet, as you can see, because they had GPUs to be used for processing. They started with 11 by 11 filter size initially in the first layer, first convolution layer, and with a stride 4. uh, so the output volume that was generated from input, the input layer was of size 227 by 227 and 3 channel image, right? So it's a very big image. So with this filter size and 96 are the total number of filters that was used in the first convolution layers. So it generated 55 by 55 by 96, which is the number of filters or channels now. So how many parameters do you expect here between these two is, if you compute, it is going to be 35,000 parameters in the first convolution layer. And in the second convolution layer, they have used, sorry, before that, the pooling layer, they have used 3 by 3 filters instead of 2 by 2 in comparison to Lenet, and stride is 2. So what will be the output size now after this pooling? So it is 55 minus 3. 55 is the actual feature map size. 3 cross 3 filter is used, divided by stride is 2 plus 1, which is equal to 27. So after pooling, the feature map size reduced to 27 by 27, and this 96 will still remain, which is where you see it here. So max pooling it's skipped. So after max pooling, again one more convolution layer has been brought in. That convolution layer has 5 cross 5 filters now, and with a stride of 1 with 0 padding attached. So to generate a output feature map of size, 128 by 128 by 256, because 256 is the number of filters. So likewise, as if you see the filter size, they have gradually reduced from initial convolution layer to the final convolution layers. So from 11, then you reach to 5, then they have reached to 3. And the justification that was given, and even they have used a lot of other architectures, and this was the one that was best suitable, is because initially the feature map size or the image size is very big. So 11 cross 11 means you are covering a good amount of region in each image by having this 11 by 11 window. If you use 5 by 5 window for 227 by 227, so that was not so efficient. But as you are filled, the feature map size reduces. As you can see here, the feature map has reduced from 227 to 27 directly at the convolution 2. So if you keep 11 by 11 filter at this level, it is very unrealistic to keep it. So it will not cover specific you know features. Instead, it will cover half of the image almost. So they have gone with a lowered filter size, and it is further reduced to 3 by 3 when the feature map size is reduced to 13 by 13. Okay, so that is one observation that you should make. And another observation is the number of filters. So if you see initially the number of filters, the first convolution layer, it's 96, meaning the output image will have 96 channels at this layer. Whereas if you go forward and see the convolution 2, the number of filters increased to 256. So it has gone to 256, and then later it has become 384. Okay. And again they have reduced. Okay. So this has become a convention even till today, and the reasoning behind is, so one, you already came to know why the filter size should be gradually reduced as you reduce the filter map size. The other observation that you should make, the why the number of filters is increasing. So as you can see, initially it is just trying to learn from edges. So lesser number of filters is sufficient. But as you go ahead at the higher layers, it is getting transformed to, a abstract level features, and you want to look at it from a different levels of abstractions as much as possible. So 256 filters means 256 different transformations are applied onto the filter map, the feature map, so that you will be able to see through from all the perspectives in all possible transformed spaces and uncover the hidden structure of the data and try to give a better representation. Okay, so that is the convention, and with the strong reasoning behind is used, and it is still, like, even today it is you know mm, been followed by the architectures, whatever researchers are trying to produce. So after the convolution, the last convolution, you see there is a pooling again applied, and this pooling, right? This pooling has reduced the size from 1313 to 56 to 66 to 56. Okay, and there they have introduced fully connected layer. They've stopped the convolution because it's already very small feature map. Then they flatten this vector. Flatten is, they convert this three-dimensional feature map into a one-dimensional feature vector just by rearranging the rows and columns into a single a row or a column vector. And then they bring in a fully connected layer of size 4096. Okay, so 4096 dimensional fully connected layer is used after the last pooling layer, and then one more FC layer, final FC layer. If you see this final FC layer, it has 1000 neurons because this was a 1000 class classification problem. That is the ImageNet database, the ImageNet classification problem that it was addressed in the competition. So ImageNet has 1000 different image categories, and hence the last fully connected layer they've kept 1000 neurons. So this is the output layer. Okay. So what it generates is the class score. So every neuron generates a activation. So if the input belongs to class 2, then the second neuron is expected to be having high activation. Okay. So that is how the layers were defined. So yeah, as I said, the retrospectives from this architecture are, it has introduced the ReLU, rectified linear unit, which is your activation function for the first time. And from that point onwards, ReLU became a most sought out activation uh, function because of its simplicity and the level of effectiveness that it provides, being so simple. And normalization layers were used at that time, and nowadays you don't see much of normalization layers, but there is a different way to achieve it though. And data augmentation. So data augmentation is something, because you know that neural networks are data hungry. So if you want better representation, better net training out of the neural networks, you should provide them with huge amount of data. But if you have less data, you can try to generate more data out of the data that is, which is your that is which is with your hand through the data augmentation process. So the data augmentation basically is like applying different simple mechanism, like so if it is an image problem, you can try to do different cropping, rotations, or flipping of the image, or even adding some noise to the image to generate more and more samples. Okay, so likewise they have applied a lot of such augmentations to generate more training data. And another notable point they have used is the dropout layer. So dropout layer is something that is used generally typically after some convolutions. So dropout is something wherein if you say dropout as zero point 0.5, meaning that in that particular layer, out of all the neurons, some of the activations are dropped with probability zero point 0.5. Okay. So this is helpful for better generalization so that if you see that your network is focusing on to a specific set of neurons and some other neurons are not getting so much weights. So that means if your neural network is biased towards fewer layer neurons in its uh, architecture, then you do not want to uh, have such network, because what happens is if your neurons are getting activated always and some other neurons are not getting activated, what happens is those neurons may be looking at a specific part of the image for the classification. So what if in the testing, or what if in the actual deployed environment, if you see a image which is having missing information, meaning if that particular feature is not available in the image, something like assume if you build a, for example, classification problem network for classifying, say, person from a car. So if the network is recognizing a person just by observing the features of his face, but not looking at any other, then if in the test environment, if there is a image that is posed where the person's face is occluded by some other object, there is some other object that has come in front of his face, then the classifier will go wrong or it will not be able to recognize, because the classifier is trained to identify that it is a person by looking at the face. You don't know, because you probably your training set has all the person images with face present. So that becomes a dominating feature and it uses it and it gets trained. So just to avoid such dependency on a specific feature or a specific portion of the object, we want to have a dropout layer wherein you forcefully try to uh, you know remove the activations of some of the neurons which are highly activated and keep other neurons coming into solution. So you forcefully try to do so that the network tries to look at any other region possible other than uh, the ones that you have made zero. Okay. And batch size 128 was used because of the computational power that they had, and they have used optimizer as stochastic gradient descent with momentum. Okay, it's a variant of what I showed you, the gradient descent technique. And learning rate they had kept as this 1 exponent minus 2 reduced by 10 manually every time the validation accuracy plateaus, means validation whenever they will keep on monitoring the validation accuracy of the model. If whenever the validation accuracy becomes static or whenever it doesn't change, they try to reduce the learning rate. And weight decay was introduced, and so they have used 7 CNN ensemble um, architectures, which generated them accuracy a loss which is reduced from 18 to 15%. So these were the important observations. Okay. Then came this ZFnet, which is a variant of AlexNet. The similar concept is used if you see. So instead of using bigger filter size, the filter sizes are reduced from 11 to 7. And in convolution 3, 4, 5, instead of 384, 384, 256 filters, they used 512, 1024, and 512. Okay. Yeah. And at the end, if you see, this is a softmax layer which converts the outputs into probabilities. And with such a notable advantages, the deep architectures were able to, win this competition called as ImageNet large scale visual recognition challenge. And if you see the very first network uh, that was the winner in 12 was AlexNet. So till then, no deep learning architectures were present. And if you see the difference between the second, you know, efficient or second most, less secure, what you can say, second network which has least error was a shallow network with error 25%. So a deep learning network with 8 layers, AlexNet had 16% error, whereas the shallow network could go up to 25% only. So that was the very first time deep learning was made so popular, and that from that onwards, the competition was completely dominated by deep learning architectures, as you can see over the years from 12, 13, 14, 15 onwards. Okay, so in 15, an architecture resonate. It was actually a network which even was having accuracy beyond human accuracy. Okay, so it was having error lesser than human error, and hence I think the competition was even beaten by the humans there at that point. So I think I'll share you these some more network details which you can go through. And one observation is over the years, what we see in the deep learning architectures is the number of layers are being increased. Okay, so today we see networks of depth 200, 250, 300 like that. And one important challenge that comes when you try to have a deeper network, even if you like have a very huge computational resource with you, you cannot go beyond some number of layers because of the problem that is inherently present in the deep neural networks, which is vanishing gradient problem. So vanishing gradient problem basically is whenever you try to back propagate the error to update the weights, right? So you do so by differentiating the loss or error with respect to the weight and adjust the weight. So if the network depth is too high, means if there are a lot of hidden layers, whenever you try to update the weights from backwards, so initial layers from the backwards will have a lot of gradient, and then the next to last will have a lower gradient compared to the previous, and again it will have lesser. So what happens as you back propagate from last layer all the way to the first layer, so at some point in time the gradient may become zero, meaning the derivative that you compute that may become zero. And at that after that point, if the gradient is already zero, there won't be any weight adjustment. That means the initial layers, however deep your network is, the initial layers may not get trained at all. They'll stop after some iteration, and the weights will not change. So even if you train for any number of iterations. So this is called as vanishing gradient problem. So this is like a problem which occurs when you try to bring a very deep architecture in place. So researchers have tried to address this problem long back, and there are a lot of solutions to it. Like do not try to make, I mean, do not allow the gradient to become zero, or if it is becoming zero, try to uh, try to make the weights adjusted weights, try to see that the weights are still getting modified by pushing some more connections, some more extra activations into it, so through the introduction of lot of other layers, as you can see. So one of such important uh, contribution was introduction of skip connections, so which was introduced in the uh, ResNet or the residual net. Okay, so the ResNet or residual net is trying to take this activation to the deeper networks, and hence it is trying to make the weight getting adjusted even if there is a gradient becoming zero. Okay, so this was the very first attempt where the network was built with 152 layer depth. Okay. So I think with this, notable architectures, I'll take you through some summary of these architectures, wherein you can see that again, yeah, ResNet with 150 deep layer was you know, uh, the architecture that has beaten all the previous architectures, even the human accuracy. Okay, so if you try to compare the complexity and uh, the accuracy with the size of the networks over the years, I can see that AlexNet was, you know, to achieve top 1% accuracy. So it was at only this much of level. Then there came a lot of other networks. So some of them were very notable, and the uh, topmost network is Inception V4 at in the year 2017. And if you see the complexity wise, so this indicates the number of operations, and this indicates top one accuracy percentage. So top one accuracy is like the very first label that the model predicts whether it is correct or not. Okay, I mean out of all the predictions, the the one that has high probability and it is correct is the top one accuracy. So if you see here, which is having less operations and more accuracy is Inception V4. So though Inception V4 is very deep, because it has introduced a lot of other modules in between. Okay, like the Inception module, which is where the dimensionality reduction is also taken care, and the gradient issues are also taken care. So they have reduced the number of parameters to, a larger extent, but by keeping the network depth to, a maximum extent. So that is how they have achieved highest accuracy, being at the less number of operations. But if you see a highly complex model, so VGG19 is the very complex model that was present, but it is still, you know, not so accurate compared to Inception. Okay, so if you see this right, so VGG had around 155 million parameters, whereas Inception have around 35 to 40 million parameters in comparison to VGGNet. Okay, so if you go deeper and deeper, it is high likely that you try to uncover a lot of, internal structures of the data, and thereby your accuracy will go high. But in a way, you will also be encountering the gradient issues and lot of other issues apart from the computational burden that you generally see. So even today, what is that researchers are trying to do is they're trying to go deeper by keeping the number of parameters less, means within their computational risk that they can take. They want to go as deep as possible, but keeping the computations less, and at the same time take care of the secondary issues like vanishing gradient and others. So that is the problem that is still being addressed. Okay, so so with all that, today if you try to summarize the same architectures, VGG, GoogleNet, ResNet, in all wide use available in different model zoos. Like if you go to TensorFlow, so, has all these networks pre-trained available with their weights. You can directly use them as standard architectures. And ResNet is the current best, as I said, trend towards extremely deeper networks. Significant research centers around designing of layers, newer types of layers, newer types of skip connections, and improving the gradient flow from back the last layer to first layer. How do you make sure the gradient will flow all the way till the first layer, so that you have that learning or the weight adjustment or the training is still continuing. Otherwise, that there is no training at all. So even more recent trends towards examining necessity of depth versus width and residual connections. Meaning that is it good to go deep or is it good to go wide? So having a layer with more neurons is better, or having a network with more layers and less number of neurons per layer is better. So such computations, such experiments are also on place. But having deeper networks with skip connections, residual connections will help you save the computational burden, whereas having wider will increase the computational burden compared to deeper. And at the same time, wider networks will not be able to see, you know, multiple transformations, advanced transformations possible, because it is at the one layer you have a lot of neural connections. But if you go deeper, it is, one transformation applied on another transformation, then another transformation. That is how the the theory and even the reasoning has been established. Maybe till today, even the deeper networks beat the wider networks, but still there is a research ongoing. So you may probably focus on any one of these, which will be a contribution to the foundations of deep learning, or if you choose to use any application, that may become an applied research as well. Okay, or you can choose an application and focus on one of these to contribute for both algorithm and as well as to your application. Okay, so if we fast forward today and see the convolutional networks, you can see their application almost everywhere and at every place where you can see a image type of data, be from classification to retrieval to the detection problem, wherein you want to detect several type of objects present in a given scene image, or segmentation, which is purely into um, you know segmenting out a specific instance of your interest. It's not just locating it, I want to semantically extract that particular region as well. So segmentation. And so other on the other side, you can also see that the hardware capacity is also being increased. So today you have very efficient GPUs and TPUs are present today for processing, and there are free GPUs available for your research. You can explore them if you cannot afford a GPU yourself. And the applications like autonomous or self-driving cars is becoming reality today because of deep learning. Okay, and even the applications like you want to recognize the action that is being performed in a given image, or you want to describe a image by sentences, that is possible. Okay, so video activity recognition is possible today. Okay, uh, so this is pose estimation. So different pose classification is possible. And if you see, it's not only limited to yes, you can see a marine application, defense applications, wherein the images of different sensor. Okay, um, so satellite image related applications. Okay, traffic applications, marine application is again a satellite image based application. So this is another application. You come out with a caption to a given image. So image captioning, look at the image and try to give a suitable caption. So this is helpful to tag the images with captions so that your search engines become more efficient, because generally we do search in our search engines by putting some query which is in textual, and you're expecting images to be retrieved matching to your text based query. So this is where this image to text conversion will be helpful, so that your retrievals are made efficient. So this is another interesting problem. And um so some of the interesting applications like image style transfer, you can transfer the style of one image onto another image to generate some imaginary images. So that is all possible today. So not only images, CNN is being used or being explored for another different types of data also, like speech problems. So they are trying to use the spectrogram, which is time versus frequency graph or the matrix, and put a time-based box, call it as an image, try to look at it as an image and try to understand from the image perspective. Such things are being explored, even the text problems. So once you represent the text into a feature matrix, now you can use that feature matrix as if it is an image with some spatial, I mean, wherever you can um, capture spatial information of your data, then such spatial information based data represented in the matrix form can be used as input to your convolution neural network. Okay. And as I already briefed, so a well-trained convolution neural network, for example, assume a ResNet architecture which is trained, you know, mm, on the ImageNet like database, which is 1 million data samples are present in it, and it is a 1,000 class database. So it has covered almost all types of objects that we see. You can leverage that learning. You can try to reuse such a very huge and well trained network for your purpose, meaning that instead of stating and trying to generate features or extract features out of image, you can directly use the trained convolution neural networks as feature extractors, meaning you take, for example, a residual network. Okay. uh, say say this is a CNN which is trained for some classification problem. Okay, so softmax is a layer which generally is used for the classification at the end. So what I do, I will remove the final layers, which is the classification layer. I'll keep till the last fully connected layer. So suppose last fully connected layer, if it is of say dimension say 756, what I get if I pass an image, I get a 750 six dimensional feature vector. Now you can directly use them as feature vector for your any other classifier. Like you can use it as a feature vector to train SVM, or even to use it as a base network for any other neural network problem. So you may be working with a problem which is having lesser number of classes. So what you have to do is you have to remove the last softmax layer which is having 1,000 categories, and replace it by a new softmax layer having only the number of categories that is present in your problem. So use that as a pre-trained you know base network, and fine tune from that point onwards. This is called as transfer learning. Okay. And in coming to the localization detection problem, you have classification plus localization, and object detection involves different three problems. It involves classification, localization, and detection, all the three. So instance segmentation is one step ahead. It gives you a what do you call it as a more semantic boundary across the object. Okay. So you can choose to work if you are trying to choose a problem for your research or project. You can definitely choose to go with one of such applications. Maybe data could be different, but the application could still be same. This will definitely be helpful. Uh, because I see that I do not have much time to cover each and every architecture here. So I'll do share with you, but do remember the core crux lies in the convolution layers and how the neural networks are trained. Okay. So yeah, any clarification so far you can raise. Uh, I'll stop sharing for a while and share back
Sir,
the
can you
notebooks.
explain the gradient vanishing once more?
Grading vanishing, right?
Yes.
Give me a second.
Hello, sir.
Hello. Yeah, yeah.
Hello.
I'm just finding a reference so that I can show you and do it.
Okay, yes, sir.
Yeah, let me share my screen. Hope you can see my screen.
No, sir. I have.
Okay.
Ah, yes. No. Yeah. Now, yes.
Yeah. So if you look at this image, right, this is a neural network. Um, so the last layer is your classification layer. Maybe it is started with some image converted into a input layer. So in the forward pass, you go on computing the dot product and do the activation, and activation will go through the next layer, and that's how it again goes to the next layer. In the same way, it goes to the last. So at this point, you compute the error, correct? So that error, there could be some error. So as you see, for example, this is a digit classification problem. If I say, that means there are totally 10 different digits, 0, 1, 2, 3, up to 9. So when I pass, for example, digit 0, in image having digit 0, I'm expecting this, you know, the output to be 1, 0, 0, 0, 0, all others are 0. Why 1 here? I want this neuron having 0 as the category label to be high and all others should be low, meaning this is the digit 0, the corresponding image is digit 0. But during your training, what happens when you pass a image, this might get, say, for example, zero 0.6 and the rest gets some different values lower than 0.6. All put together, the total value is 1. So what is the error now? So you compute the difference between the vector that you have arrived with the expected vector. The expected vector is 1 followed by all zeros, right? Whereas the obtained vector is 0.6 followed by some different fractions lesser than 0. So you compute the error. You just you know compute the squared error, for example, in this case. So you get one value. So squared error is one. I mean, what's that? Mean squared error, for example. So mean squared error is a loss function. I compute the loss or error. Now, what is required? You want to make sure that the sample, when you pose it to this network which is having 0, you want this neuron to come out high, I mean close to 1, all others to be close to 0. So there is a error. Why the error has occurred? Because the weights are not so good in generating 0, I mean high value for this neuron. So I try to adjust the weight. So when you adjust the weight, so this weight gets updated, this weights get updated, and this weight gets updated. All the layers from starting from last layer back to the first layer. So in doing so, in the back propagation, if the network is very deep, say assume having 10 layers. So you start from the 10th layer, update the weights in the 10th layer, okay, and then you have some gradient left to be updated for the ninth layer. Okay, then you update the ninth layer, then you come to the eighth layer. The gradient is already very low in the ninth layer. So gradient means the error. So because these initial layers from the last will get lot of gradients for updation. Whereas when you come here, the gradient value is less. When you come here, the gradient value is even more less. So if the network is very deep, say 10 layers, so 10th layer will have higher gradient. They get updated. Means whenever there is a gradient, meaning when you differentiate the gradient with respect to weight, you get some value, and that value you can use to update the weight. When the gradient itself is low, the differentiated value will even be low, and you whenever you try to use that and the factor of it, then that value is very close to 0. That means the old weight and the new weight, the difference is very small. And after certain iterations, after certain layers from back to the initial layer, you will see that the gradient has already become close to 0. And whenever the gradient is close to 0 or actually 0, then the weight will not update. So if you recollect the weight updation function, so this is the weight updation function, right? This is the old weight, this is the gradient, correct? and this is the learning rate. So if this value is low, if this value is low, fraction of it is even low, and when you subtract this value by a low value in the sense, for example, it is 0.0001. So volt weight minus 0.001 is not that different from the W volt. So this is fine. Say assume you are in the fifth layer from backwards. When you come to the fourth layer, this will already be even more smaller, close to zero. When it is close to zero, or if it is actually zero, then whatever fraction you apply, that is zero only. So W old minus zero is W old itself. Then W new is equal to W old, meaning the weight has not been updated in that layer. So if it starts at say sixth layer from last, then the seventh, eighth, ninth, or you can say the initial layers of your network, the initial layers of your network will not train at all. Will not get trained at all means their weights will not be updated. If the weights are updating, then only you call it as it's getting trained. If the weights are static, then there is no change. And if there is no change in the weights, then the network will not train and your training will stop at that point. So that's called as a vanishing gradient problem. Okay.
Okay, sir. Thank you.
Yeah. Maybe you can look through. And there is one more problem called as exploding gradient, meaning if the gradient value is very high, so what happens is why the gradient goes low and low is because if the gradient is already low, this will be multiplied by the weight here. So that will get reduced. There is a chain rule that is applied. So the chain rule, because of the chain rule, the gradient value becomes smaller and smaller. So if you try to understand back propagation in a better sense, so back propagation will take the value and it gets multiplied every time, and because of the multiplication, so if you are multiplying two smaller values, say two fractions, the result will be a smaller number than the two, correct? If you are multiplying two numbers which are more than say 1, then you get a value which is even more bigger. So if it is 0 point something and 0 point something, the result that you get is lesser than 0 point, I mean lesser than both of them. So in that sense, the value goes low and low if the initial gradient is already small. Okay, so try to understand chain rule, then probably you will have a better understanding of why the gradient goes low and low over the layers from last to initial layer, and hence the gradient becomes close to zero and the weights will freeze, and that's called as vanishing gradient. Okay, I think I've given you sufficient pointers. Probably you can explore further. Um, yeah, so that's about it. Now let me take you through a couple of examples. I'll ping this on the chat as well, so you can also run it through and see. So it's a standard example from Keras, or maybe this is in my drive. It's not possible. Anyway, if you're unable to open it, let's leave. I'll give you the other one. So as I just wanted to show you how to build a simple neural network, a CNN based architecture, and train it. So the different libraries that we use is Keras, TensorFlow basically. They are now interchangeable. Okay. Um, I'm trying to build a classification model, a CNN architecture for classifying the MNIST data set, right? So it has 10 classes in 10 digits. And MNIST is a standard data set available in the TensorFlow already, so you can import it. So if I run this too, and MNIST, once you import, you can load the MNIST data. So it already has both training data and test data. So you can use train data for training purpose, and later, once you have trained the network, you can use test data to validate it. So as you can see, it has downloaded the data set from the Keras website. And if I show you, So it has 60,000 images, each of size 28 by 28. Okay, so this is already available to you for directly uploading and sending it. I mean using it for you for your purpose. And similarly, test set you can see, and if you see the white train is the category labels. So each sample has a category. So if you see white train of 0, it gives you one label. So 5 means this corresponding image has the digit 5. Okay, so category 5. So this you can use to train a network directly. There is some no normalization that I'm applying, trying to normalize the inputs in the range 0 to 1. Originally they will be 0 to 255 because they are all pixel values. So just to have lower values, reduce it to 0 to 1 scale by dividing by 255 and convert the values from the nominal values into categorical, because it's a classification problem. You want the expected output in the last layer to be a vector with 1 for the neuron of your interest and 0 for all the other neurons. So for example, if this is 5, that gets converted into a vector, a 10 dimensional, I mean 1 cross 10 vector. I'll show you now what is white train of 0. So this is a vector now with 0, 0, 0 in all place, but 1 in the fifth location, and again 0, 0, 0. Meaning that you are expecting in the last layer 10 neurons, and when I pass in this first image, I'm expecting the output to be 0, 0, 0, 1, 0, 0, 0, 0. Meaning the fifth neuron should be high and all the other neurons should be low. So that when the network gets trained to produce this, later I can interpret back this as 5. Okay, so that's how the categorical, so this is called as one hot encoding you have to generate. So this can be directly possible if you use nputils.to categorical by passing your labels. Okay, and coming to this location, I'm trying to define the CNN architecture here. So CNN architecture, you can directly use the Keras different layers. So I'm trying to build a sequential model. So wherein you just go on attaching the layers to that model. So initially create a model called as sequential. It is empty network now. I first add in the first layer. So I'm adding in directly a dense layer which takes my inputs. I mean, there'll be input layer, for example. So the input that you pass is the input layer. Then comes this dense layer. So this dense layer is accepting your input layer pixels, which is 784. Originally they are 28 by 28, and I've converted them to what? A vectors shape. So from matrix 28 by 28 to 1 cross 784. And kernel initializer is, so what is the initial weights that you want? So instead of randomly initializing, you can pick it from a specific distribution, say normal distribution, or you can choose it from the Gaussian distribution. Okay, so choose it as a normal. I've chosen it, and activation for this layer I've used ReLU. Okay, and um, after this, I'm trying to add one more dense layer, which is going to be my classification layer. Okay, that means the number of neurons in that layer is going to be equal to the number of classes. So number of classes is, if you see, it is 10. Okay, so this will have 10 neurons in this layer, and for this also I'm initializing the weights from the normal distribution, and the activation I've kept it as softmax because it has to generate the probabilities. Okay, so the layer which you decide to be your classification layer in the multi class classification problem, then you have to use softmax as the activation layer at the end, so that the outputs are converted into probabilities. Okay. So what loss you want to use? Categorical cross entropy is the loss I've used. Uh, Cross entropy loss is generally used for the classification. When it is multi-class classification, it's a just variant of the binary cross entropy is categorical cross entropy. And the optimizer is the gradient computation function, which is ADAM, adaptive momentum. It is SGD variant itself. And what metrics you want to track over the training? I want to track accuracy. Okay, so this is how you create a model, and you can choose to go with different layers also. So let's try to see. So I've defined it as a function, and I call that function to generate a model, and you can use dot summary to see the architecture information of this model that you've just created. So this will take input, which is your input images, right, and connects it to a dense layer, and hence this has 61,544 different parameters to be trained, and from that dense layer you connect it to one more dense layer with 10 neurons. Okay, so that you generate the probabilities for 10 different categories. Okay, so this has 7850 number of parameters to be trained. So the total number of parameters here are 623 290 to be trained over your training process. So once you generate this model, I mean create this architecture, now you can call the fit function wherein the actual training will happen. So this fit function expects the data and the targets. Target is nothing but your output. So your training data and their category labels. You pass both of them, and the validation set you are passing it, so that for training it uses the training set, and to show you the accuracy on the validation set after every epoch. Okay, it uses this validation set, meaning it will pass this X test after one epoch and see what are the generated outputs and compares it with the expected output and computes what is the validation accuracy. So it gives you training accuracy and validation accuracy both. So accuracy on the training set and accuracy on the validation set. So which should you choose to? The the model is called as a good performing model if both training and validation accuracy are high. So your validation accuracy is the one that you should be focusing at, or even the loss. You can add a loss also as one of the parameters to track. Okay, and number of epochs is how many iterations you want to pass through. So just to show you quickly, I've used two iterations, but generally it will not converge into iterations. You may have to go a little more number of iterations, so depending on the problem. Batch size I've set as 200. You can modify it, and verbose is 2, means it's like different display parameters. So if I run this, you see that, so it is in the first epoch, meaning in the first iteration. So at a time it passes 200 samples in the forward pass. Okay, and it computes the gradient, means it does the weight updation. Then next to 200 samples, weight updation, those 200 are randomly selected in the training set. That is the reason why you see that this 300 out of 300, because it is running on GPU. It is so fast, and the size of data is also small, so you are not able to see. But it has, in the first epoch itself, it is running 300 forward passes and weight updates. Okay, why 300? If you see totally there are 60,000 data points or samples in your training set, divided by 200. So you get 300 subset. Each subset is one batch. So after passing one batch in forward pass, one back propagation happens for the weight updation. Then the second batch goes in. Again, weight updation happens. So likewise, all the 300 batches will go in, will to complete the first iteration. And after all the 300 batches have been covered, this is the accuracy for the entire training set, and this is the loss for the training set. Whereas this is the loss for the validation set, this is the accuracy for the validation set. So we can see that training accuracy is lesser than validation, means it is generalizing well. So the network which is trained here with the training data with this accuracy and loss is able to perform equally good and even better than that for the validation set, which is unseen samples. Okay, so it has taken 5 seconds per epoch and 17 milliseconds per step, in the sense for batch. In the second epoch, it starts from the weights that are complete generated in the first epoch. So it again starts the second scanning of the entire data set. So that means, and again 300 batches are created. Each batch is passed, backpropagation is done. In a way, you're trying to further train the network to do better and better, and hence you see that the loss is still reduced and the accuracy is improved for training, and validation loss also reduced, validation accuracy is also improved. So this is the expected behavior of your network when you try to train it for your problem. So if everything goes good, if your architecture is, you know, fitting for your problem, then you are generally going to see this kind of output. And you may probably stop after some iterations when you reach out, say 99 point something, or if you see that the validation loss is less than the expected validation loss, something like you have set a threshold of I want to go up to validation loss being 0.0001, then you can choose to set so many epochs. So if it is possible, it will go, or it, what may happen is, if you keep too small loss, it may go till that point and it may try to get trained again, and hence the weights will again get disturbed and the loss may increase from that point. So try to see the point where the loss is minimum for your architecture and stop at that point and freeze those weights, and that is the end of your training. Now, once you have completed the training and fixed it, now you can use that model for the prediction purpose. So I'm just pushing the same test set for the prediction here, trying to compute what is the error that it is generating. So this is the X test, I mean the samples, the expectations, and compute the different scores. Okay, so it computes different scores. Basically, error is one of them. Okay, I think yeah. So that is how you can do it. I'll ping this. This is the collab link. The other one has the drive link, which I had to give permission. Probably you can use this now. Hope you have understood how to build a simple network. Okay.
Sir,
Anyway, I'll
will you
question.
please show some plots, sir, to make it interesting, like for accuracy and loss or this thing?
Sorry.
Will you please show some plots, sir, like some sort of graphs mentioning error rate and this accuracy?
Yeah. Anyway, loss and accuracy are as a part of these outputs. You can use them to draw your graphs of your interest. That's up to you. What is essentially required is how you can construct a network and how you can train it, and scores at the end anyway. So whatever score that you get, because it is not the score that you are getting multiple accuracies here, it is just one accuracy that we have obtained. So you can do a confusion matrix estimation by using the outputs, and using the confusion matrix you can generate the different curves that you want. Okay, so I have another example over here on the MNIST itself, but it's a slightly different model, making use of convolutions, because in the previous network, if you see, I've not used any convolution layer at all. I've directly used the dense layers and directly have taken the input as the input feature vectors. So you can open this notebook in your browser and you can run through along with me. So essentially here it is the same problem of MNIST digit dataset classification, 10 classes, and the input shape is 28 by 28 image. Okay, So from the same Keras datasets, I'm trying to load the data, and I'll apply similar normalization. I mean the scaling stuff. Okay. So and also trying to convert the data, I mean labels into categorical ones. So try to execute these two cells. Okay. And now in a similar fashion, let's try to build a network, but in this case, let's try to use convolution. So for the convolution layer, you have to use conv2d from the Keras layers. So as you can see, I've imported Keras layers. So from layers, you can use convolution 2D, max pooling, all of them. So start with the input layer, which takes in the input matrix converted into a feature vector, because I've reshaped it previously, as you can see. Uh, yeah, so this is where the reshaping has been taken care. So this goes as a 784 dimensional vector, and it will be 60,000 samples that are going in. So convolution 2D is the 2D convolution function in Keras layers. So here the different parameters are, so if you look in, so it's a 2D convolution layer. What it expects generally is the number of filters, input shape. So filters, so how many filters you want to keep. So in our case, we have kept 32 filters, okay, for in this convolution layer, and kernel size, meaning the filter size, as 3 by 3, and activation function we have used relu. So what it does, it gets added as the first convolution layer after the input layer. Okay. Then we have tagged a pooling layer, which is max pooling. So max pooling, as you know, it is used to reduce the size of the feature map by using the max operation. So pool size is the filter size for this pooling. So we have taken 2 by 2 for this. So convolution pooling followed by one more convolution, but in this time it is 64 filters with the same kernel size, and again activation value. One more pooling layer with same 2 by 2 pooling, and this flatten layer is to convert the 2D feature map into one dimension. It's just the reshaping, and after you flatten it, we have applied one dropout layer so that generalization is achieved. As I briefed, what is dropout? Dropout is to drop the activations of a layer by probability 0.5. Okay, so almost like you can assume 50% of the activations will be dropped, so that if the network is focusing on a particular region of the image, so you want it to uh, avoid looking into only a specific region and focus on all the remaining regions as well, so that if the in the test time, if you get a data which is partial or occluded, then also the network should be good in performing well on such type of partially occluded data sets. So that's the reason you use dropout. And finally, I want to do the classification. So I have kept the dense layer with softmax as the activation. Okay. So dense layer has number of neurons equal to the number of classes, which is 10, and activation is softmax, so that I generate probabilities. So if you try to see the architecture wise, you have a convolution 2D initially, which takes in, I mean, the result of this convolution operation is a 26 by 26 feature map, such 32 channels output. I mean, such 32 feature maps will be generated because you have set the number of filters to be 32. And there are 320 parameters to be learned. See, as you can observe here, the number of parameters is very less for convolution. Whereas in the case of, you know, dense, it is very high. So even if you can observe here, we have one dense layer with just 10 neurons. So here we have so many neurons compared to the dense layer, but still the number of parameters is 320. This is the advantage of having convolution, wherein you are spatially selecting the neurons to be connected, whereas in the dense it is a fully connected. Yeah, so fully connected layer is same as dense layer. So you call it as interchangeably in Keras and TensorFlow. It is called as a dense layer, meaning every neuron is connected to every other neuron. Okay. So max pooling will not have any trainable parameter because it is just it will have a window of 2 by 2 and goes on choosing the maximum out of it. There is nothing like training required or parameter to be computed over there. And one more convolution layer wherein we have used the kernel size again 3 by 3 and this time 64 filters, and hence 13 by 13 is reduced to 11 by 11 after convolution, and this will have 64 channels in it. Okay, and when you see the number of parameters, it is 18,496 because this is connecting these two uh, layers. It has 32 channels, it has 64 channels, and hence the number of connections increase. Again, max pooling, which will reduce the image size to almost half of it because we have kept the pooling size as 2, and number of filters or number of channels will not change, and no trainable parameter. Flattening will just convert this a you know a 3 cross 3 or 4 cross 3 matrix into a single dimensional vector. So 5 into 5, 25 into 64 is 1600. So you get a one dimensional vector of 1600 length, meaning in this flattened layer you'll have one uh, layer with 1600 neurons which get connected to a dropout layer, so which will drop the activations by the probability 0.5, mean 50% probability, and then a dense layer connecting to this dropout layer. So 1600 neurons connect to 10 neurons in the last layer. So 1600 into 10 is 16,000, plus each neuron will have one bias. So 16,010 is the number of parameters. So totally this network has 34,000 parameters here to be trained during the training process. Okay. And that is how the model is constructed, the network is constructed. Now if you want to train it, you have to first compile it to see if anything is wrong in it by passing certain parameters like what loss you want to use. And generally for multi-class classification problem, in the sense you have more than one classes to be classified, then you use loss as categorical cross entropy. If number of classes is only two, then binary cross entropy is sufficient. For the regression problem, you may choose to uh, go for mean squared error as the loss. That's sufficient. And optimizer, there are a lot of optimizers which are variants of standard SGD optimizer, which is stochastic gradient descent. So Adam or Nadam or Adaboost, there are a lot of such optimizers. Probably you can explore further to understand each of them and tracking accuracy and loss. So fit is the training function as we have seen before. Let's try to see. As you can see, it is going through each patch, and because it is bit higher dimensional now, it is, I mean, it's a bigger network. So as you can see, over the iterations, it is the loss is getting reduced. So if you further explore the Keras model fit function, it has some callbacks that you can make, wherein you can also ask the model fit function while training. You can log this into some file, or you want to draw something, you can ask for that as well. So all those detailed stuffs are available in the Keras model function. So you can dig down further. Yeah, basically this is how you build it. I think the number of epochs is 15. Let's leave it like that. So that is how a simple convolution neural network can be built. Okay, so it is so for the first time, if you are doing, you need to understand what each layer is and what each layer is trying to accept. And basically, we've understood the concept of each layer already. So try to decide. So in deep learning, you have to come out with the architecture, one thing, and the hyperparameters. So hyperparameters in a deep convolution neural network is the number of layers, types of layers, and at every layer, what should be the number of filters and the filter size, what should be the activation function, okay, and you know. Uh, so another is what should be the loss function, what should be the optimizer that you use, okay, what should be the batch size and number of epochs. So these are all called hyperparameters. So why these are all hyperparameters? Because you need to set it, and maybe in a single attempt you may not get a best set of hyperparameters. So you try to systematically work with several combinations of these hyperparameters. So just list down what are the different hyperparameters that you want to fix from your side. Training weights is like the network will take care of it from the back propagation and forward propagation. But in the case of hyperparameters, you create a table of the hyperparameters, and against each hyperparameter you set different values. So now you can write a program to loop across the different values for every hyperparameter and come out with a training and then a best uh, set of hyperparameters which has resulted in very least loss or very high accuracy should be chosen and finalized. So that's how you can try to automate that. And today if you see, we are talking about auto ml and lot of other no code uh, no code ml tools which are helping you in doing this, which pretty much do this, like depending on what data that you push in, they select few of the known architectures in the literature which are already pre-trained and available, and they use those architectures onto your data, and they decide the hyperparameters, means they work with different hyperparameters, means there'll be lot of parallel trainings happening with different sets of hyperparameters and different architectures. Ultimately it comes out with one architecture with one best set of hyperparameters that is giving you the best results. So that is what those tools generally do, but they'll help you to only some extent to reach out to a best combination. But from that point onwards, if you want to go further and increase, it is you who have to sit and understand and analyze what is the where is the room for improvement, whether you want to change and tune the architecture itself, add in some layer, remove some layer, or maybe um, change the loss function or define your custom loss also is possible. So for your problem, you can define your loss, right? You can try to do so instead of using standard loss functions. So those are all the avenues for your research that you can look through. So if you come out with a loss function for a problem at your hand, and if that loss function can be used across different problems, then that's a very huge kind of contribution that you can give to the community of research. Okay. And in the neural networks, you also see a type of neural network called as autoencoder, which is generally used for unsupervised learning. This autoencoder is kind of architecture where you don't, if you, for example, if you think that you do not have a classification problem, meaning you do not have a supervised learning problem, um, where there is no label data set available with you. You have a data set, you do not know what sample should be classified to which category. Then you want to go with, say, for example, clustering, but you want to do the feature extraction and clustering through neural networks. So what you can do is you can try to use autoencoder in such a case. Autoencoder, the input and output are going to be same. You keep the image as input, and in the output also you keep the same image, and you build a network of deep layers in between, and you ask the network to train itself to take this input image and generate the same input image as output. Okay, so while doing so, it learns a best efficient representation of the image that is possible, and later you can use that representation for your clustering and other purposes. Okay, and the autoencoder is not only limited to such applications, but also it can be used for image denoising purpose. So you keep a noisy image in the input, noiseless image in the output, and you're trying to ask the network to learn how to eliminate this noise from this input image and generate this noiseless output image. So if you have both noisy and noiseless images, you can generate autoencoder which learns how to remove the noise automatically, right? So all such things are possible. So this autoencoder is one such example for noise removal. Okay. So similar pre-processing, and here we are trying to induce the noise onto the images to generate noisy image in the data set. Okay. Okay. So the data preparation, pre-processing all goes same. So here only change what I'm trying to do is in the same input data for every image, I'm trying to induce some specific noise into it. Okay, so that I use noisy image as input. As you can see, this noise image is with salt and pepper noise, and this is the original image. My expectation is I give this image as input and I ask the network to generate this image as output. So both your input and output layers will have same number of neurons, right, which is equal to the number of pixels in the image. Okay, whereas the input image, if this is the input image, I keep the output image expected is this, and I ask the network to train. So if you can see this simple architecture, I went on generating, adding up layers, starting with input layer, which takes in the input noisy image, then a convolution layer, pooling layer, convolution layer, pooling. So this part of the network, which goes on converting the image into features, is called as encoder. Later, at some point of time, after having some convolution and pooling layers, you try to now, because you know that generally the convolutions will reduce the size of the feature map. And after this step, the image, the feature map size is very small. Now you want to go back to the same size, the original size of the image. So instead of doing the convolution 2D, you do the reverse of the convolution, or you can say 2D convolution transpose. Okay, and when you do the transpose of the convolution, it is something like deconvolution that happens. So in the deconvolution, you can see that I'm trying to increase the filter size, the sorry image size back to the original, and at this stage the image size, the output network size will become the input layer size. See here, the input layer has 28 28 1, and output layer also has same 28 28 1. But in the deep layers, if you see, it is 28 28 32, then 14, then 14, then 7. And from that point I started with transposed convolution, which is deconvolution, or you can also use upsampling, which is also possible. So deconvolution layer, one deconvolution layer is increased from 7 to 14, then 14 to 28. Then I applied one final convolution to convert this 32 channel feature map into one channel feature map. And finally, this you can use it as a architecture. you give the training data in X, and in Y also you give the same training data because you're expecting the network to understand the features. So here I'll do twice the training, once with the same input and output, and second time I'll pass in the noisy, and in the output I keep the actual images. So you see here in the first training, it is trying to just understand and represent the images, whereas subsequently I again do one more training wherein I pass input as noisy training samples, which is where we have induced the noise ourselves, and in the output I keep the actual noiseless samples and ask the network to train itself again, so that it understands how to remove that noise from it. Okay, so I think it is having a lot of epochs. Probably you can run through offline. I'll share this in the chat. You can take you can run it through offline yourself and see how the noise removal is possible. Okay, and similarly, this another runbook has a way to visualize what neural networks are trying to learn. Let me see if I can run through and show it to you. Yeah, herein I'm not training any network. Instead, I'm trying to use the network, the pre-trained network, which is ResNet 50 V2. So trained on the ImageNet dataset. So include top as false, meaning I don't want the classification layer. I want only the model except the last layer. So, and I'm going to extract the feature map from this layer of the ResNet 52. So you can extract a specific layer out of your network from the model by using the get layer function by passing the layer name of your architecture. Okay, so once that is done, I'm probably, what I'm trying to do here is I'm just sending in an image and trying to see the feature map generated at that particular layer. So this is how the feature map looks like. Okay, and using that feature map you probably can try to visualize. How many are there? So you can try to visualize where exactly your network is trying to see in your um, training process. Okay, so I think we are running out of time. So I'll have a couple of more notebooks which I'll share it along with the slides. Probably you can go through in detail. There is sufficient documentation also present to understand what each step is about and try to replicate them. Okay, to see how and what this each architecture is about. Okay,
Okay,
yeah.
sir. Thank you. Thank you very much. Participants, you can respond if you want to ask anything. Still, you have
You
a
can take a
doubts.
couple of time, a couple of
Yes,
minutes
yes.
to discuss. Otherwise, you can also drop me a mail offline so that I can respond to you if it is something taking more time.
Sir, please write your mail ID, sir, in your chat box. Participants takes the mail ID of the Suhail, sir. Can also contact later if you have still doubts.
Sir, I have one doubt, sir. Uh,
Yes.
sir, how to choose the number of filters or filter size in a CNN, sir?
Yes, that's what is the hyperparameter that you have to work with. But you can look into the literature and try to understand with respect to a problem similar to yours, what type of architectures have been used and what is the filter size generally used. But one recommendation, as far as I even have understood, is typically the number of filters will be less in the initial layers, and gradually you go on increasing them. And the filter size actually, the feature maps, the filter size basically, right? The filter size should be kept less. I mean, not should not be more than a kind of 7 or 9. Okay,
Okay, sir.
start with maximum 9 and go on gradually reducing it.
Okay, sir. And
Yeah,
one more question, sir. Is there any difference between deep neural network and deep learning?
deep neural
Both are
network,
same?
yeah,
Mm.
both are same. Deep neural network is the algorithm, whereas the concept or the theory around these deep neural networks and training such deep neural networks is called as deep learning. I think.
Okay, sir.
Okay,
Okay, sir. Uh,
fine, madam.
thank you, sir.
Yeah. So,
Any,
sir, if there are no
okay, okay.
concerns, we can stop at this point. And anyway, I've dropped my email in the chat. Anybody, if has anything, can share and
Yes,
reach
sir.
out to me.
Please share the PPTs also. I will forward to the
Yeah, I'll
participants.
do share it. Yes.
Okay, okay. Okay, sir. Thank you very much. Mohammed Suhail, sir, Technical Manager from Standard Chartered Global Business, Bangalore. Covered a neural network topics, in a very clear-cut manner, elaborate examples, so very patiently. So started with a very basics. What about what is a neuron, its architecture, and the different types of functions, how that output will be calculated. Very basics. Even people who don't know about the neural networks also can understand easily. So that much basics are started, and later he covered different types of neural networks and deep learning, predefined deep learning networks like Alexa, Google Net, ImageNet, and the corresponding architectures. Explained in a detailed manner with examples and also shown a hands-on using a Colab, different nets. I hope everybody learned about the neural networks and enjoyed the 3 sessions. So, very patiently and clearly explained. Continuously speaking 3 hours is not an easy job. So we have to thanks for her for his patience. On behalf of the Department of Computer Science and on behalf of the participants and on behalf of me, uh, thank you, sir. Heartfelt thank you. Thank you very much, sir. We hope we are expecting your future, your cooperation in the future also. Thank you, sir. Thank you very much, Sohail, sir.
Thank you very much, sir. It was a nice session too, and there were a lot of interactions, which
Yes, yes, sir.
of
Yes,
course,
yes.
made me happy. And it is always good to have the interactions, which keeps the sessions active, and even for the speaker to have the same kind of
Yes,
energy
sir.
level
Yes,
throughout
sir.
the session.
Right,
Very
yes.
happy that you have a very good set of participants attending it. And anyway, it's happy moment always for me to come back and present in CUK's events. So we'll look forward to the similar events in future too.
Sir is coming next week also, right? Next,
Hopefully, in the last week, I think
uh,
there are some more sessions.
yes, yes,
Yeah,
21st onwards, one more is there.
yes, sir. Looking
Okay.
forward to meeting you again, sir. Thank you so much,
Okay,
and
sir.
to all the participants and to the organizing committee of this event, and to the CUK. I express my heartfelt thanks and happiness for providing me this opportunity.
Thank you, sir. Thank you very much.
Thank you so much, sir. See you soon.
Thank you,
Bye.
sir. Okay, sir. Participants, all of you fill the feedback form. It is posted on the chat box. We successfully completed 4 days and one more day remaining. And tomorrow we have an exam. So you may send exam link after the first session itself, so that you can submit before the last session. You can take one time and submit. It will consist of a multiple choice questions only. Manas, are you there?
Yes, sir. Hello, sir.
Yes.
Okay.
Anything else, Manas?
Nothing else, sir. That is Jaya only. We cannot find her name
Not
in the
contacted,
registered
no?
participant. Yes, sir.
One of the participant joined with name Jaya, and that name is different from the registered name, so we are unable to calculate the attendance of her. So please contact me or Mana so that we can rectify it and we can do good to you. If you are not responding, you cannot do anything regarding the attendance and the marks also. That's it. Okay, we'll meet tomorrow morning, 10 o'clock. Thank you all. Okay, Manas.
Okay, sir. Okay.
Thank you.
Thank you all. Thank you all.
Thank you, sir.
Thank you, sir.
Thank you all.